picking up at looking at two half cells. When you connect two half cells, the important thing to remember is the more positive E or potential, the more spontaneous it is as it's written. Same thing with thermodynamic. If you flip the equation, then you change the sign on the potential. There is a big difference, though, when dealing with potentials, in that in Hess's law, if you multiplied the equation by 2, you would multiply the enthalpy. That is not the case with potentials. Potentials do not get multiplied if you happen to multiply an equation so that your when you add them together, the appropriate things cancel out. Okay, but the important thing to note is that the more negative the potential, the more readily something is oxidized. These are when they are written as reductions, which is typically how they are written. So when your half cell reaction or your half redox reaction is written as a reduction, the more negative the potential, the more readily that component is oxidized, and the stronger the reducing agent. Okay, the more positive, the more readily it is reduced, and it is a stronger oxidizing agent. I'm hoping I said that right. Hopefully go by the words, not by what I'm saying. Okay. All right. And remember, all are written as reduction half reactions, so the oxidized reaction, half reaction, is the reverse. Right. We already talked about the standard hydrogen half cell. Let's take a look at this problem just to work through one. We've got that the overall equation here, the potential of the cell is 1.1 volts. If we're given that the standard reduction potential of zinc plus 2 to zinc solid is negative 0.76, calculate the E for the reduction of copper to copper metal. Well, let's write what we know here. We have zinc plus 2 electrons going to the zinc metal has a reduction potential of negative 0.76 volts. If we look at this overall equation, we see that if we have zinc solid plus the copper going to the copper ion in solution and the copper metal with an overall of 0.11 volts. If we were to take this and break it into its two half reactions, I would have zinc going to zinc plus 2 electrons, and then my copper being reduced to the solid copper. The reduction of the plus 2 zinc ion to zinc metal is negative 0.76. So if you look here, this is just the reverse. So this must be 0.76 volts. We're looking for the reduction potential here, so we'll call that X. We know that when we add these two, we get the 1.1 volts. So 1.10 volts is going to be equal to 0.76 volts plus X. Solving for X, we get a positive 0.34 volts, which is the answer. And that's how you would use standard reduction potentials with a redox equation to calculate potentials. Oh, didn't mean to do that. Okay, so the strongest oxidizers have the most potential reduction potentials. The strongest reducers have the most negative reduction potentials. The greater the difference between the two, the greater the voltage of the cell. Okay, now let's talk about electrolytic cells. What happens if we made the current go backwards? Could we do that? How? Well, we could by attaching a power supply, right? And if you have any of those batteries that you plug in to recharge, that's exactly what you're doing. Main differences, or actually let's review a voltaic cell real quick here. And something like a voltmeter, in this case we're going to use the energy from the spontaneous redox reaction to light a light bulb. The electrons travel towards the cathode. In the cathode, or at the cathode, is where reduction occurs. This is it's the positive electrode. Cations are attracted to the cathode. Yeah, that's right, because reduction occurs there. All right, the electrolyte, this allows movements from one electrode to the other. I need my salt bridge to continue the flow of negative particles this way, positive particles flow that way, cations. At the anode, oxidation occurs. It's marked with a negative, okay, and electrons go on the outside. I'm not exactly sure why I have those in the notes. Okay, so what we can do with, oh, I think I missed something. Hold on. So let's look at an electrolytic cell. Sorry about that. All right, electrolytic cell. Here we have the anode represented by a positive. Oxidation still occurs here. Okay, electrons are flowing towards the cathode, same as the voltaic cell. Cathode reduction occurs, but the sign does change, right? But red cat and an ox still apply. Again, the electrolyte anions flowing this way, cations flowing that way to complete the circuit. Okay, so major differences are the direction of the electron flow. Cathode and the anode switch. Oxidation, though, still occurs at the anode. Reduction still occurs at the cathode. The cathode is now the negative electrode. The anode is now the positive electrode. And a power supply is needed because the reaction is not spontaneous. The salt bridge is also not necessary. You will see it, but you can do electrolysis in the same physical container. You do not need the salt bridge. Okay. What do we use electrolysis for? Well, electroplating, putting a coating of a metal on some cheaper metal like chrome plating. Reducing pure elements, that requires the molten salt. Producing sodium hydroxide, that would be an aqueous solution. That's where we're going to end. Let's look at some factors that are going to affect the electrolysis products. Charge on the ion. The less mass produced when an ion must be reduced from +2 to a +1 because it takes twice as many electrons. So the charge on the ion is going to affect the electrolysis product. The current, high current, more mass produced because there's more electrons being transferred in a given amount of time. And then of course time, how long do you run it? Let's take a look at just some quick electricity terms. Ohm's law, voltage is equal to the current times the resistance in the circuit. Charge Q is coulombs. one electron carries 1.6 times 10 to the negative 19 coulombs. You have your voltage, which is joules per coulomb. Current, charge per time. 1 coulomb per second is 1 amp. And then your resistance. Just to throw out standard shorthand notation for a voltaic cell. This is not universal. Typically your anode goes first. Okay, and that would be this half cell. It would be your anode. Okay, so flow of electrons is going to go left to right. Dashed lines in the middle represent the salt bridge. So in the anode you have oxidation, hydrogen losing electrons. In the cathode you have your ion being reduced to the neutral metal. And that's just kind of a random factoid. So electrolysis of aqueous solutions. You have your electrolyte, which is the reactant in the process of electrolysis, and you have things that are discharged. Ions are said to be discharged when the charge is removed. Okay, again, the electrolytic cell. How do we predict products in electrolytic cells? First thing is to identify all of the ions present in the electrolyte and to which electrode they would migrate to. Check the reduction potential chart for the species that can be reduced. Those will go to the cathode. Okay, check for those that could be oxidized. Look for the ion that will be discharged. You're going to look for the potentials. Okay, the more positive, the more spontaneous it is. Write the equation for the net reaction and then try to determine what the changes would be observed at each electrode. What is going to affect the selective discharge during electrolysis? The relative potential of ions, the relative concentrations of ions in the electrolyte, and the nature of those electrodes. Okay, we've done a lot of examples in class. I would suggest you look those over. Okay.